Hi, so for today we're going to talk about statics of rigid bodies, addition of planar forces. So this is my very first video in the statics of rigid bodies, and we're going to start with vectors, forces, how to add forces, getting the resultant, okay, by component method or even triangle rule, parallelogram law, okay. So let's get started. So addition of planar forces, okay. What is a force? A force is simply a push or pull, what we have learned in physics. But here we're going to study here in statics the deeper meaning of a force. A force represents the action of body on another. So if you apply a force to a certain particle, right, you are actually having an action of one particle to another particle. Okay? So, it is generally characterized by its point of application, magnitude, and direction. So, as you can see, later on we will be talking about what is a vector. Again, a force is a vector, meaning it has a magnitude, okay, can be represented by the length of the vector, and the direction of the vector can be represented to where it is directed, okay, by an arrow head. So, its unit includes a Newton. Okay, for an SI unit of the force, we have the Newton. For the English, we have the pound and the kilopound, the kip. Okay, it means if we see a value of 8 kip, okay, 8 kips, that corresponds to 8 kilopounds. Okay, so we define the direction of a force by its line of action and the sense of the force. So line of action, as you can see here in our image below, the line of action of a force makes an angle with a given fixed axis. So for example, we have a particle A here, and it is acted upon by a force of 10 pounds directed into this direction, okay? Directed into this direction with a certain reference to what we call a fixed axis. So as we can see here, we have a reference fixed axis here, which is the positive x-axis, let's say, okay? That is 30 degrees from the positive x-axis. So meaning, this force is characterized again by its line of action with respect to the fixed axis. Okay? With a given fixed axis. In this lesson, we will always be dealing with the fixed axis. Where does the force is referenced? Okay? But in our discussion, we will by default always use the reference for any forces as the positive x-axis. So as you can see here, we have a fixed axis of which the force is acting upon, okay, on this particle with respect to a reference fixed axis. So the line of action is this, and actually the sense of the force is directed outward that particle. Okay? Whereas in this we have the same line of force or line of action. Still the fixed axis is 30 degrees, but okay, the sense of the force is now directed toward the particle. So we can always define the force, okay, the direction of a force by its line of action and the sense of the force. So, what are vectors? Vectors are actually defined as a mathematical expression possessing both the magnitude and the direction. So, which add according to the parallelogram law. Okay? So, vectors are quantities that has a magnitude and direction. So, such vectors can also be, some common examples are displacement, we have the acceleration, we have the velocity. Whereas if we get a negative velocity, it only means that if we are talking about two-dimensional motion, negative velocity means you are heading, if you chose the positive x as the positive velocity, the negative x as the negative velocity. So, negative velocity means you are going on the negative x-axis if that is motion in one dimension, okay? Or motion along a straight line. If it is free fall, okay, if you choose positive y as the upward, okay, or positive axis of the coordinate and the negative y as the negative axis of our coordinate, meaning negative acceleration or negative velocity, let's say it's a free fall, corresponds only that the velocity is going downwards. And of course, that is the direction. Okay? So in terms of magnitude, magnitude is the in acceleration due to gravity, that is the 9.8 meters per second squared. But actually its direction is always going down. Okay? So a vector is represented by an arrowhead. Okay? We have an arrowhead or head or bold-faced type. In this book, I think we are using the bold-faced type to represent vectors to differentiate it from a simple variable. Okay? So as we can see here, we have two vectors. Okay? So the equality of vectors, equal vectors have the same magnitude and direction even if they have different points of application. If two vectors have the same length of the arrow, okay, and that corresponds to the magnitude, and that vector heads toward the same direction, then we can say that those two are equal vectors. Okay, so the length of this arrow represents its magnitude. Okay, and the arrowhead actually denotes where it is going, the direction. Okay? So that if we have P here, if we wish to negate the negative of P, we want to find the negative of P. Negative in vectors only means that we are going to change the direction of the vector, such as in this case. So we have here a vector P in this direction. If we negate the negative of this vector P, we only what? Uh, change is its direction, okay? The opposite direction, okay? So, addition of vectors. Vectors can be added according to parallelogram law or triangle rule. As we can see here, if we have a particle A here, it's acted upon a vector P in this direction, vector Q in this direction. We can always get the sum of these two vectors if we are going to, again, project this vector Q onto this and project this vector P onto this and draw a line, okay, from that A, particle A, up to the point where these two vectors meet. That is the parallelogram law, thus forming a parallelogram. So, we have also the triangular rule of vector addition. For example, we still have the same given vector P and Q. What are we going to do is we will use the tip to tail method. Okay? So what will happen is that if we have a particle A here, okay, if we choose this P, okay, to be stationary in its original position, I can freely move this, okay, vector on the very arrowhead of the P, so that this vector P and Q are now connected. Okay, and if I'm going to get the sum of these two vectors, I'm going to draw an arrowhead or a line from the very initial vector, tail of the vector, up to the arrowhead of the last vector. Hence, I have P plus Q vector. And of course, you can also choose Q, okay, to be stationary. And then I'm going to move P. As long as you are not changing the magnitude and the direction of the vector, you can do that. Okay? So that this P, I'm going to what? Connect it to the arrowhead of Q. Okay? And it points it toward here. And getting the resultant or the P plus Q of the vector, still we have the same P plus Q. And this P plus Q on our figure B is the same as in figure A. So that's how we resolve some vectors. Okay? So the sum of two or more vectors can be found by arranging all vectors in a tip-to-tail fashion. Okay, that's what I'm trying to say. And then connecting the tail of the first vector to the tip of the last vector. So for example, we have three vectors now. We have three vectors P, Q, and S. If we wish to find the vector addition of the vector P, Q, and S, first, okay, I'm going to have my P here, okay, whether Q is acting here, okay, and S is acting here at the same particle, we can always get the sum of that force acting on this particle by the tip-to-tail fashion or method. So what are we going to do? So we have P here. Okay. Oops. So I have P here. I'm going to connect the other vector Q here from its arrowhead. Okay. Tip to tail. Okay. So tip to tail of the first vector to the second vector. And again, I have another vector S here. So I'm going to connect the tip of Q to the tail of S. And how am I going again to get the addition or the P plus Q plus S vector? So from the very first tail of the first vector, which is P, up to the last arrowhead or what do you call this? Tip of the last vector. Okay? So, it doesn't matter the order. You can always choose. You can first choose P, then Q, then S, or you can choose P, S, and Q. Okay? You will still be arriving at the same answer. Okay? So, here we have P, Q, and S. We have S, Q, and P. Okay? So, it doesn't matter. You will still arrive at the correct answer. Okay? So, product of a scalar and vector, multiplying a vector by scalar changes the vector's magnitude, but not its direction. Well, of course, if we multiply a vector to a scalar of which the scalar is -1, it will reverse its direction. Okay? So, if, for example, we have a vector P here, and we multiply a scalar multiple of 1.5 to our vector. So as you can see here, if we multiply it, it becomes this vector. It only shows that this vector P is now actually what? Twice or 1.5 times, okay, this vector is 1.5 times larger, okay, than this, okay? So 1.5 times P. So, in other words, if we multiply scalar by our vector, we are only changing its magnitude. Okay, so we are only changing its magnitude, never its direction. But if the scalar, okay, if the scalar involves negative, then definitely, for example, as this, then definitely the direction of the vector will be reversed. So in this case, we have this vector P, we have this -2 of P, okay, -2P, we multiplied -2 by our vector P. So what happens is, because of the negative sign, it reverses direction. And because of the 2, this magnitude or the length of this is now twice of this, but opposite direction. That is the product of scalar and vectors. Okay, resultant of several concurrent forces. So let's try to consider the image here. We have consider a particle A acted upon several coplanar forces, meaning those forces lie on the same plane. So since the forces all pass through this particle A, the forces are said to be concurrent. Okay? So we have a concurrent force because all of the forces pass through the particle A. So we can always represent, okay? We have three forces here, P, Q, and S. We can always represent these three forces, okay, into a single force, what we call the resultant. Okay? The single force R has the same effect on particle A, which is called the resultant. So again, how do you find the direction of the resultant and the magnitude of the resultant? By graphical means, we can use the polygon rule. So we have, let's say, if we want to get the resultant of this, okay? So again, choose again a first vector. In this example, we chose P, okay? And we're going to move this Q vector such that its tail is connected to the tip of vector P, which is this, okay? And of course, we have also would want to move this, not changing its direction, not changing its magnitude, okay, such that the tail of vector S is now connected to the tip of vector Q. Hence, we have P, Q, S. Okay? And to draw the resultant, okay, we need to draw a line or a vector emanating from the very first tail of the vector P up to the very last, okay, tip of the last vector, which is S. So this is now the resultant, the resultant force. So these forces, PQS, can always be expressed again into a single force, what we call the resultant. Okay, so the effect of these forces on particle A, okay, has the same effect caused by this resultant on particle A. Okay? So, resolution of forces into components. So, conversely, if we are given a resultant force F, we can always resolve it into what we call components. The components of a resultant, okay, is actually its decomposition from the resultant to many forces. So the process of substituting them for F is called resolving the force F into components. So if we are given a force, okay, if we are given a certain force or a certain resultant, not plainly lying along X, not plainly lying along Y, but is in the first quadrant, okay, we can always resolve the force into its component. Okay? We have, in case of two-dimensional, we have the X and Y components here. So, in this example, we have three possible sets of components for a given vector F. For example, we have this F. This is the Y component. This is the X component, okay? For this sample, again, this is the another component, okay? So if this is the axis, that's why I've said if this is the axis followed by P and Q, that is the X and Y axis. But if it's not, okay, if it's still straight here, then definitely that is still the X and Y component. So we have here another set or component of a force, and then of course also this. Okay, we can always resolve that force into its component. Okay, so let's try to solve some problems. Okay, so two forces P and Q act on a bolt A. Determine the resultant. Okay, let's try to determine the resultant of that. Okay, we have two forces P and Q. P with the 40 newtons, Q with the 60 newtons is acting on bolt A. This is the bolt, okay? The point or the particle of which the force is being acted upon. Determine the resultant, okay? So the resultant is actually found by the following solution. We can use the triangle rule, the parallelogram law, resolving these two forces into components, then getting the summation of f of x, forces along x, summation of forces along y. Okay, but let's try to use our concept of trigonometry in order for us to solve this problem. Okay, so I'll try my best to have a good drawing. Okay, I'll really try my best. Okay, so now we have, oops. So we have, if you're going to draw that, we have this force of which that is the Q, 60 newtons, okay? And if I'm going to draw again this, okay, this is the x-axis. I can label that as our x-axis. And this is the P, which is actually the 40 newtons. And we have a 20-degree here, and this is 25 degrees. So if I'm going to draw this as our y-axis, okay, so this would be our point A. Okay, so how do we find that? Again, we can actually redraw, okay, we can actually redraw this representation as this, because we can actually what, vectors can be moved freely as long as you are not changing its magnitude and direction. So, let's say that this is your, okay, this is your force P. This is your x-axis. So, this would be 20 degrees. This is your force P, 40 newtons. By tip to tail, I'm going to again, what? Going to move this vector on the tip of the very P. Okay? So, of the P. Okay? So, by that, I'm doing what? Okay? So, this should be now our Q is equals to 60 newtons. And if I'm going to draw the resultant, this is our point A. If I'm going to draw the resultant, this must be from here to here. So, this must be the resultant. Okay? That must be the resultant of the force because that is technically adding the vector P and Q. So that, now I have to find that resultant. Okay? And of course, I should have a, let's try to uh, arrange this first. Okay? So, take note that this 25 degrees is still this 25 degrees. Okay, this is still the 25 degrees. Okay, so we have here the P which is equal to 40 newtons. Okay, we have this 25 degrees with respect again to P. Okay, so the problem is how are we going to find the resultant R? Well, of course, okay, we can get the angle of this. Okay, we can get the angle of that. Let's label that as theta. Okay. So, given the figure here, as you can see, this is an imaginary reference, okay, emanating from P. This is actually what? If we're going to extend this, get the angle, okay, this is a straight line. Get the angle from here to this, that is actually equivalent to 180 because that is a straight line here that is slanted. So, that is 180. Okay? So, if I'm going to get the angle, so what will happen here? I have a straight line. Okay? 180 degrees. That is 180 degrees. Okay? And I have here, what? Okay? Another vector around here. So, that is my vector Q. 60 newtons. That is 25 degrees. So, I mean, I can get the angle. That is the theta. So, if I'm going to get the angle, theta is now 180 degrees minus 25 degrees. And theta now is 155 degrees. So, why do I need to get the theta? Okay? Because upon getting theta, okay, upon getting that theta, I could actually use what? I could actually use, okay, I could actually use the cosine law to find R. So why do we need to get the angle? Because if we draw it again, okay, we will be forming another triangle. Okay, this is a triangle of which this is our P is equals to 40 Newton. And now this would be our Q is equals to 60 Newton. Remember, the length is the magnitude. And we have R here, which is the unknown. And we have the angle here, theta. So if we get the resultant by cosine law, okay, by cosine law, we simply have R squared is equals to P squared plus Q squared minus 2PQ cosine of the included angle, which is 155 degrees. So, when going to get R, that is simply what? We have 40 squared plus 60 squared minus 2 times 40 times 60 cosine of 155 degrees square root. Well, of course, because that is R squared. So, if we evaluate that, our resultant should be, okay, 97.73 Newton. Okay? So, that is our resultant force. Okay? How about the direction or the angle with respect to the positive x-axis? Okay? So, this angle, what is this? what is this angle? Let's say that is alpha. Okay? So again, if we're going to redraw again our triangle, okay? Let's say that is our triangle. I'm so sorry, I'm really not good. Not that good when it comes to drawing. Okay? So this should be our, let's try again another one. Okay? So this should be our angle. Okay? So our resultant is, this is your P, this is your Q, okay? This is your R. So this is equal to 40. This is equal to 60 newtons. Okay? What I'm about to find is this angle. What is this angle alpha? Okay? So, again, what is that angle? I know that the theta is 155 degrees. Okay? And if I'm going to, I have this R of 97.73 newtons. If I'm going to find the this alpha using sine law, okay, so that is sine of A, okay, sine of, I mean alpha, let's try, okay, sine of alpha over the opposite of that, that is 60 newtons, okay, the opposite, sine alpha opposite is equals to what? Sine theta, this theta, the opposite which is over r. So we can get alpha by cross multiplying this. So we have arc sine of the 60 sine of theta which is 155 over the resultant which is 97.73 newtons. So if you get that, make sure that your calculator is in terms of degrees, that is 15.04 degrees. So that is not, this is that angle. Okay, but what I'm after is the angle it makes with respect to the positive x axis. And this is our positive x axis. So, if this is, according to our problem a while ago, if this is 20 degrees, okay, I could get that angle, let's call beta. Okay? So, now, the beta will be simply 20 plus the alpha, that is 20 plus 15.04 degrees, and that is equivalent to 35.04 degrees. That should be our angle, okay, of the resultant. Okay? So let's continue our discussion. So sample number, problem number 2. I've copy pasted here. Okay. So two tugboats are pulling a barge. If the resultant forces exerted by the tugboats is 5,000 pounds force directed along the axis of the barge. This is the barge. Okay. The axis of the barge is here. The horizontal line here. Okay. Determine the tension in each ropes. So definitely have a tension here. Tension 1, we have a tension 2 here. Okay, given that the alpha is 45 degrees. This alpha is 45 degrees. Letter B, the value for alpha for which the tension in rope 2 is minimum. Okay, so we will again try to draw. Okay, this is the representation. This is the point B. Okay, of our problem here. Okay, so as you can see here, we can derive some relationship. This is T1. Okay, this is T2, tension 2. So the problem is asking for tension 1 and tension 2. So this is 30 degrees from the resultant. By the way, this is will be our resultant because it says in the problem, okay, that the resultant is 5,000 pound force directed along the axis of the barge. This is the axis of the barge, okay, of which this is the axis of the barge, okay, which is 5,000 pounds. So if I'm going again uh, to derive this, okay, tension 1, this is tension 1, tension 2. I can copy this, okay, on the other side, which is this is the tension 2. I can also copy this vector on this side. This is the tension 1. So that, why do I need to copy that? Because I have to find the tension 1 and tension 2. In order for me to find that, I need to have one triangle. Okay? In this case, the upper triangle or the lower triangle. Okay? So, again, we have 30 degrees here. We have 45 degrees here with respect to the axis of the barge. And of course, this is 45 degrees because we have a vertical angle here. 45, so this must be always also 45. And this is 30 degrees, so this must be also 30 degrees. So, if we're going to go, okay, if we're going to draw, again, the triangle, the lower triangle, okay, so we have here, we have an angle of 30 degrees. This is our resultant, okay, which is 5,000 pounds. And this is our alpha, okay. This is 45 degrees. And we need to find, definitely to find this angle. Okay, this is T2. This is now our B, okay, point B. This is our T2. And this is our T1. But it's also equivalent to this because I move this vector on this side. Okay, so this is still T1. Okay, I need to find theta by fact that triangle, the sum of the angles of triangle is 180. So this theta is 180 degrees minus 45 plus 30 is 75 degrees. So theta is now 105 degrees. Okay? And again, we can easily now find the T sub 2 and T sub 1 by using sine law. So by sine law, okay, by sine law, it says that first T sub 1, okay, T sub 1, and this is the opposite angle to T sub 1 over sine 45 degrees is now equal to, let's say, T sub 2, T sub 2, the opposite angle to T sub 2, side of the T sub 2 is 30 degrees. It's equal to sine 30 degrees. And it's also equal to what? Okay? Resultant, okay, R, over the sine of theta, of which it is opposite. Okay? Sine of 105 degrees. Okay? So, how can we solve? We can solve by first T sub 1 over sine 45 degrees is equal to R over sine 105 degrees. So if I'm going to cross multiply that, that is R sine of 45 degrees over sine of 105 degrees, equivalent to 5,000 pounds sine 45 degrees over sine 105 degrees. So T sub 1 therefore is now equal to 3,000, if we're going to solve that, 660 pounds. Okay? How about T sub 2, sir? T sub 2, sir, we can also use the same relationship. T sub 2 over sine of 30 degrees is equal to R sine of 105 degrees. So getting T sub 2, we have what? 5,000, that is the R, pounds, sine 30 degrees over sine 105 degrees. So our answer should be, okay, 2,588 pounds. But the book says 25, okay, 2,590, 2,590. It's a pretty close value, okay? So here we can have this answer. That is the tension for each rope. We already use sine law. Sine law only in determining the tension in each rope. Okay. How about letter B? B. Okay. So find the minimum value, the value of alpha, okay, for which the tension in T sub 2 is minimum. Okay. So, the value of alpha, this alpha. Okay? So, as you can see, we have T2 over sine, okay, T2 over sine 30 degrees is equals to R over sine of 105 degrees. Okay? And that's equal also to T sub 1 sine 45 degrees. Okay. So if I want to make T sub 2 minimum, I have to what? I have to let this sine 105 or this angle, which is the theta, okay? Theta, this theta, equal to 90. Okay? If I'm going to make this equal to 90, and if I'm going to get T sub 2, okay, let's say T sub 2 is over sine 30 degrees, R over sine 90, we all know that sine 90 is equals to 1. So therefore, if I'm going to get T sub 2, okay, that is R sine 30 degrees. So that is 5,000 pounds sine of 30 degrees. And that is equivalent to 2,500 pounds. Okay? So, if I'm going to make the theta, okay, theta 90 degrees. So, this is 90 degrees. This is still 30 degrees. So, definitely, the alpha now would be 60 degrees. Okay? For which the T sub 2 is minimum. Why? Because if I'm going to sine 105 is uh, less than 1. So R over a certain value of less than 1, that would actually give you what? A higher number than R. But if we're going to set 90 degrees here, okay, such that if we're going to get T sub 2, we're going to get a minimum value, okay, rather than a maximum value. So as you can see here, 2,500 pounds. So our answer should be alpha is 60 degrees. So why do we say that this is the minimum value of T sub 2? Okay, again, because you can see from here, the original value is 2,588 pounds and we have 25 pounds. So let's say that if we are going to let this angle, okay, let's call it 2 prime T2. We're going to make that this angle again less than 90. This is a greater than 90. We see T sub 2, okay, which is actually max, okay, or not a great value greater than this, okay. So if we're going to make this, okay, a value less than 90, let's say, I'm going to make it sine of 80 degrees, okay? And I cross multiply this. This is R sine of 30 degrees, okay? So we have 5,000 pounds times sine of 30 degrees over sine of 80 degrees. Let me just compute it. Okay, 5,000 sine 30, we have sine of 80, okay? We have 2,538 pounds. So 2,538 pounds. So as you can see here, if we increase the value of this, okay, we not let this equal to 90, still the tension in T sub 2 is not minimized. The only way for this to be minimized is when if we set this angle theta into 90 degrees, because sine 90 will always give you 1. Sine greater than 90 will always give you what? Greater or less than 1. Okay, so if you divide R by less than 1, then you are increasing the R. Okay, therefore you are increasing also T sub 2 because you're going to multiply it with sine 30. Okay, unless if this is 90, okay, you can get the minimum T sub 2. Okay, and of course, if you set this theta as 90 degrees, then the value of alpha will change because of this relationship. So this is 90, this is now 30, 120, 180 minus 120, that is 60 degrees. And I hope you understand the concept there. So let's continue. Okay, let's continue. So we can add forces by components. Again, this is component. I'm so sorry. So a force F can be resolved into a component f of x along the x-axis and a component f of y along the y-axis. So if we are given a certain force in this direction with a theta with respect to x-axis, with the reference point, fixed axis, so we can decompose this f into its f of x. If we're going to project this on the x-axis, this would be the component of the force F in the x-axis. If we're going to uh, uh, resolve this force into f of y, this should be f of y. Okay? And again, if you tilt again the axis, it's still applicable. We can always resolve the forces of a certain force in x and y in terms of components. So, we have what we call the unit vectors. So, two vectors of unit magnitude directed respectively along the x and y axis are called unit vectors. So, these unit vectors represented by I and J, bold, okay, bold face I and J. So they are called the unit vectors, and they have a magnitude that is equivalent to 1. Okay, so we can always express any vectors into its unit vector for simplicity of the calculation. Okay, so again, the scalars f of x and f of y may be positive or negative depending upon the sense of f of x and f of y respectively. So these terms, f of x that is not bold, okay, in bold face is different from the bold face f of x and f of y. If we are talking about a not bold face f of x and f of y, we are talking about the scalar quantity. But if we have a bold face f of x, f of y, we are talking about the vector components. Okay? So again, where the scalars f of x and f of y are called the scalar components of the force f. So, of course, if we have the vector components f of x, we can rewrite this as equal to the scalar component multiplied by the unit vector I that denotes that it is going on the x direction. And of course, we can actually get the vector components f of y is equal to the scalar component fy multiplied by the unit vector j to denote that it's going on the y-axis. So, of course, if we put them together, we can get the very vector, okay, of force, and that is the equivalent to the sum of these two vectors. Okay? So, this f is different from the magnitude of the given vector. This component or force vector is actually in terms of its vector components. So, this is not the same as the magnitude, because the magnitude requires us that we're going to get this by Pythagorean theorem, the square of the f of x and square of the f of y, and get the magnitude of this f. Okay? So that is a different thing. So it means if we have f of x here, let's say 2i, so 2 units, okay, I, okay, in the direction of the x direction, and fy 2, let's say 2i plus 2i plus 2j is actually a vector that is 2 units away from the origin x-axis. In x-axis, this is I, and in 2 units away from the x or from the y, or from the origin to the y-axis. Okay, so that's the meaning of that. Okay, if you want to find the scalar components, we can use the following formula. F of x is equals to the magnitude of the force times the cosine theta, where theta is the any angle, the value of angle from 0 degrees to 360 degrees. This theta, in most of our discussion, we will be using the reference as the positive x-axis reference for our theta. So, Fy, okay, the scalar component of y is equal to F sine theta. Okay? So, they define this angle, define the signs of the scalar components. So, f of x and f of y can be negative and positive depending on the direction of the our force. Okay? And that direction is indicated by from 0 degrees to 360 degrees. Okay, so let's try this example. So, a force of 800 Newton is exerted on a bolt A, as shown in the figure. Determine the horizontal and vertical components of the force. Let me just copy that. Okay. Oops. I'm going to copy this and paste it here. Okay. Let's try. So, we're going to find the component of this vector force 800 newtons. So, let me just again make myself clear. This is the x-axis, okay? This is the positive x-axis. Okay, so this is the angle given, 35 degrees. But this is not the positive x-axis. So what I'm going to do is to find its angle with respect to the positive x-axis, and I call it theta. Okay? So, if this is 35 degrees, if this whole horizontal line is 180, then definitely my angle would be 180 degrees minus 35 degrees. And that is equivalent to 180 minus 35, that is 145 degrees. Okay? That is the theta I'm going to use, okay, to get the f of x, okay, and the f of y. This is sine theta. Okay? Okay. So, I have now the magnitude of force, which is 800. I can simply substitute, okay? Remember, I'm getting here the the vector component, okay? Horizontal and vertical component. So, if I'm going to get that, so I must have an I here, I have a J here. Okay? Vector components. So, we have the magnitude already, which is 800. So 800 cosine of 145 degrees I in terms of x direction. So I have 800 sine of 145 degrees here in terms of the y direction. So f of x or fx vector component is equal to what? Negative 655 newtons I. Fy, vector Fy, we have what? 459 Newton J. Okay, why is this negative? The x, because if we resolve this force into the x-axis, it's going into this direction. So, negative. And if we resolve this into y-axis, it's going upward, then positive. So, the force actually defined by the vector components is actually negative 655 Newton I plus 459 Newton J. Okay, this should be our force, vector force. And this is the components, vector components. Okay, for this problem. Okay, let's try to solve another one. So, but before that, okay, we have here a uh, another slide. Okay, so it says, when a force F is defined by its rectangular components, f of x and f of y, we can always find the angle theta defining its direction from. And again, when I say theta here, okay, this formula, okay, this theta is always with respect, again, to the positive x-axis whenever we use this formula. Okay, tangent theta is equals to the f of x over the f of y. These are now what? Components, scalar components. Okay? We can obtain the magnitude of vector force by the formula, okay? Component of x squared, okay, plus force component of y squared. Pythagorean. Okay? So, let's try a problem. Oops, let's try the problem. Try to solve. Okay. Okay, a force of 700. This is in terms of vector, 700 pound. Why do you know? Because it has a bold-faced I here, plus 1,500 pound J is applied to a bolt A. Determine the magnitude of the force and the angle theta it forms with the horizontal. The horizontal, the problem is talking about is the positive x-axis. So this is the theta, okay? As you can see here, okay? So we are given a vector component of force. How do we find the magnitude? The magnitude is simply f of x squared plus f of y squared. So what will happen here is 700 squared. This is our fx plus this is our fy, 1,500 squared. And the magnitude of that force, if we are going to solve this, that is equivalent to 1,600, okay, 55 pounds. Okay? And the direction is, of course, inverse tan or arctan f of y over f of x. As you can see, the components only. So, arctan Component of y is 15 pounds over 700 pounds. So the angle it makes with the horizontal axis, well, of course, it has to be less than 90. The answer is 65 degrees. Okay? So this would be our answer for this problem. Let's try to solve another problem. Okay? We've skipped this problem. Okay, I'm so sorry. I'll try to copy this and let's try to answer. Okay? So, a man pulls with a force of 300 newtons. This is the man. On a rope attached at the top of the building. This is the rope. As shown, what are the horizontal and vertical components of the forces exerted by the rope at point A? Okay? The vertical and horizontal components of this force. Well, of course, according to our given, okay, this force, okay, that is the man exerting on the rope is 300 newtons. That's the magnitude of the force, no doubt. Okay? So we are to find the Fx and the Fy here, vector components. Okay? So, the problem is we don't have any angle and we have here the alpha, but we know that the horizontal distance is 8 meters from the man and the vertical distance from the rope or from this point A is 6 meters. So, if I'm going to get the angle alpha, I'm going to have a tangent, okay, function here, tangent of alpha. Tangent is TOA, opposite, which is 6, over adjacent, which is 8 meters. Okay, if I'm going to get alpha, I want to get that because I want to have an angle here, because definitely I will be using that theta here. Okay, and then I don't have the theta. Okay, so we have 6 meters over 8 meters. Meters will cancel. That alpha is actually 36.87 degrees. Can we use that alpha? The answer is yes. Okay? But directly using that alpha, you might forget the sign. Okay? Because this alpha is in reference with the x-axis. That's correct. Okay? But with this, we have a theta that is always with reference to the positive x-axis in the counterclockwise direction. This is now in clockwise. Okay? So, we can use this, but let's stick to the definition of our theta. Okay? So if this is alpha, if this is 36.87 degrees, okay, can I get the angle from the positive here down to here? Okay, can I get that angle? Okay, because that's the definition of our alpha or of our theta. So if I'm going to get theta here, so that should be this whole rotation or revolution is 360. Okay, am I correct? So this whole rotation, that is 360. Okay, I have to minus it with 36.87 degrees. Therefore, I can get the angle of that as 323.13 degrees. And now, we can get the components. So, we have 300 cosine of 323.13 degrees. We have 300 sine of 323.13 degrees. We're going to evaluate that. Well, of course, this is 240 newtons I. Okay? Minus 180 newtons I. Let's take a look at the signs of f of x and f of y. This f is actually in the fourth quadrant. Okay? So, its x should be positive, correct? And its y should be negative. Correct. Okay, correct. Then, the force is actually what? 240 newtons I minus 180 newtons I. Okay? So, sir, you said a while ago that we can also use 36.87. Yes, we can also use that. So, let's try to use f cosine of 36.87 and f sine 36.87. Okay? You try to solve this. This is f 300 cosine 36.87 and f here is still 300. So what will you get? So we have 300 cosine 36.87. That is 240 newtons. Same, correct? How about the other one? So the sine. So we have sine 36.87, which is 180 newtons J. Okay. Technically, the x's are the same. Okay. But the y, okay, f of y, this is f of x, and this is f of y, are not the same because this is negative and this is a positive. That's the danger of directly using the alpha. Okay? So you can use alpha if and only if after the computation you have to apply the proper sign. Okay? Proper sign. Because your force here is in term of fourth quadrant, its x should have positive and its y should have negative. Okay? Unlike if you're going to stick with the definition of theta that is from the positive x-axis measured counterclockwise, okay? So you'll arrive at the what? The very correct answer without actually locating where that force is located in the quadrants. Okay? I hope you get what I'm trying to say. So you really have to be careful in using this alpha. Okay? To be safe, you can use the theta. You can always use that. Okay, let's try our last problem for this video, for my statics, okay, video. So let's try, okay, let's try this. Four forces act on both A, as shown. Determine the resultant of the force of the both. Okay, the resultant. As we can see here, we have F1, we have F2, we have F3, we have F4 acting on the both. So how do we solve that? First, many forces, okay, we're going to find the resultant. So you can create a simple table. We have force here, we have x component here, we have y component here in terms of Newton, both in terms of Newton. Okay, so we have force 1, force 2, we have force 3, we have force 4. Okay, in order for us to get the resultant of this, is we are going to resolve all of the forces into x and y components and add all the x components and y components and then get the magnitude of that force, okay, as well as its direction by the formula, again, a while ago, by the formula fx squared plus fy squared, in this case, summation of all the x's, and we have theta as inverse tan, summation of forces along y, summation of forces along x. Okay? So first, let's resolve all of these forces. Okay? Let's resolve all of these forces into its x and y component. Okay? So if we're going to resolve all of these forces into its x and y components, so we can what? Do this. So for F1 of x, component of x, okay, we have this F1, 150 newtons. That is equivalent to cosine of theta with respect to the positive x-axis. That is 30 degrees, right? We can get the y component of the first force, 150 sine, okay, 30 degrees. So as we can see, the result of this is positive 129.9 Newton. And this is 75 Newton. So this is 129.9. This is 75 Newton. For F2, okay, for F2 we have, this is our force 2. 20 degrees in the y-axis. Okay? Our theta there, okay, F2x, okay, would not be 20. Excuse me. Because as what I have said a while ago, our reference should be always on the positive x-axis. So if this 20 degrees, if this is 90 degrees, okay, plus 20, that is 110 degrees. So F2y the same, 80 sine of 110 degrees. So the result of this should be negative 27.36 Newton. Okay? And this is 75.18 Newton. Okay? So negative 27. This is 27. Negative 27.36. And this is 75.18. How about force number 3? Okay? F3x, we can get, as you can see, F3x is lying plainly on the y-axis. Okay? So, its x component is 0. So, for F3y, okay, that is still the same. Okay? It's going downward. So, we have 110 Newton sine of how many degrees? Since it is in this direction, this is 90, this is 180 plus 90, that is 270 degrees. Okay, and you may be surprised that it is negative 110 Newton because it's going downward. Okay, so here we have 0, we have negative 110, okay, and lastly, for our fourth component, okay, in terms of x, we have 100 cosine of the angle with respect to the positive x. Positive x. So, what will happen since this is 15 degrees below the positive x? So, we have 360 degrees. We have to minus it because our reference is always from the positive x up to here. Okay? So, 360 excuse me, minus 15. And f4 of y is 100 sine 360 degrees minus 15 degrees. Okay? So our answer here, for the x component, we have 96.59 newtons. We have negative 25.88 newtons. So we can write it here. So 96.59. Okay, and then negative 25.88. Okay. So, can I erase this? Okay, can I erase this for a while? Took a picture or snapshot of this so that I can add this. Okay, okay, okay. I'll try. Oops. So, as you can see here, we have already resolved all of the components. Okay, all of the components. This is 96. Okay, over 59. So we can get the summation now of the x components. So if you add, excuse me, if you add all of this, so what will happen? This should be 199.13 newtons, and all of this summation of f of y, of course taking into account the negative signs. Okay, so that should be 114.3 newtons. And if we wish to get the magnitude, okay, the resultant force, okay, whether it is a magnitude or not. So this is simply 199.13 Newton I. This is the vector component in terms of x plus 14.3 Newton J. Okay, so this is the vector components. How about the resultant? This should now be the resultant, not the F itself. That is the denoted by R. The magnitude denoted by two parallel lines of the resultant is simply what? The square of this x component plus the square of the y component square root. Okay? So what will happen here? This should result to 199.6 Newton. Okay? And the direction, don't forget the direction. Okay? The direction is theta arctan, okay, of summation of Fy over summation of Fx. So our result would be arctan, okay, arctan of f of y. What is our f of y? This is 14.3. Make sure you are in degrees. Okay. So our theta would be 4.1 degrees. Again, this theta is actually always reference with respect to the positive x-axis. And that's it. I hope you learned something in our first video about statics. So very sorry for my cough, okay? And very sorry for my not so little good drawing, but I hope you learned something in statics. Thank you so much and God bless.